All right, today we're going to be talking about nomenclature of alcohols and reactions of alcohols. We're going to shove them both together in the same lecture because I think we can get through all that in the time we have today. So let's talk about some properties of alcohol. What are their physical properties? In terms of their properties, they're really, really similar to the properties of amines. Remember amines last week we talked about they have the NH2 group. Amines are capable of hydrogen bonding, right? And alcohols contain an OH group. OH group is also capable of hydrogen bonding, right? So therefore, their properties, in terms of their physical properties, are pretty similar. The OH is capable of hydrogen bonding. So in other words, we're going to have much, much higher boiling point for an alcohol than, say, an alkane, because this has hydrogen bonding, right? Whereas an alkane doesn't. It's just got London forces. And also, they're going to be soluble in water so long as the chain is 6 or less, right? Around 6 carbons, solubility kind of goes to around 6. That's kind of the magic number. Just like with amines, right? With our chain length, remember if the chain gets too long, then the effect of the nonpolar region overrides the effect of the hydrogen bonding, right? So that's why around 6 carbons, the solubility just kind of falls off the cliff. So here are two, I just made these kind of off the cuff, right? Hydrogen bonding and ethanol, right? There's its boiling point at 78.5. It's a liquid at room temperature. Where here's ethane, right? Ethane has London forces only. So if you're comparing ethanol to ethane, right? Ethane is just you yank off this OH, put that hydrogen back, right? It's a gas at room temperature. It boils at -42 versus 78.5. That's a humongous difference. And the solubility increases with the number of OH groups. Okay, so if you have one OH group, that's soluble. But if you've got 2 OH groups, that's going to be even more soluble, right? The more places you have where you can have hydrogen bonding, the more soluble it's going to be. Also, this would have a much higher boiling point, right? The one with the 2 OH groups is called a diol. This one's going to have a much higher boiling point than the one with just 1 OH group. So how do we name alcohols? It's really easy. Our parent chain must contain the OH, just like with amines. Right, last week when we named amines, we had to make sure that our parent chain contained the amine. Here, our parent chain needs to contain the OH. Our suffix becomes all, right? That's the suffix. And then we're going to number that parent chain to give the OH the priority. So in other words, if we have the choice between making a methyl group have a low number or making an OH group have a low number, we're going to choose to give the OH group the smaller number. And then we're going to use numbers to locate where the OH group is in that chain. And then if this is a cyclic molecule, we're saying that OH is carbon number 1. Now because this is elementary organic, we're only going to name molecules with 1 functional group at a time, right? So I'm not going to worry about naming a molecule that contains both an amine and an OH, okay? We're only going to deal with 1 functional group at a time in elementary organic, just FYI. Now also one more thing to talk about is that, remember we talked about how with the alkenes and alkynes and amines, you could split the suffix, right? You can do the same thing with alcohols as well. So let's do this one together. All right, so this is a 4-carbon chain. Now here's the choice. I could number it 1, 2, 3, 4 and have the OH get the lower number. Or I can number it 1, 2, 3, 4 and have the methyl group with the lower number, right? The alcohol gets higher priority than any other substituent. So if that were chlorine or bromine or whatever, right? The OH group is the lower priority, the lower number, higher priority. Now, we can then just make this suffix butanol, and then there's a methyl group on carbon 3. So the name is 3-methyl-2-butanol. But also I want to show you both methods, right? We can also split this up and name this 3-methyl-butan-2-all, right? You can split the suffix. Your textbook leaves it together, right? It puts 2-butanol, and that's perfectly acceptable. But some other textbooks will put the 2-all as the end, okay? So either one's acceptable. Your homework should accept both. Most students prefer this method because that's what your textbook uses, right? And it's just kind of easier to say this than it is to say this, but they're both acceptable, okay? Are we good on nomenclature here? All right, if you understood amines, then alcohols are a walk in the park. Because unlike with amines, we have N-ethyl and all that good stuff, we're not going to make any modifications to the alcohol. Like last week when we did amines, we talked about regular amines versus modified amines. We're not making any modifications to the alcohol, so it's really easy to make. Now, if it's a ring, by default, the OH gets number 1 status, right? And then you just need to decide how to number. Do you number clockwise and go 1, 2, 3, 4, 5, or do you number counterclockwise 1, 2, 3? You'd obviously go counterclockwise, right? So 3-methylcyclohexanol. Be good on aiming it in a ring? Okay. So let's just take a second and practice. I'll pause the video, give you a chance to try. All right, let's go over these. So we need to decide longest reaction and where we're going to number from. Obviously, we're going to number from the right. Yes, because if we number from here, there are no other substituents, and this needs to have priority. So we number 1, 2, 3, 4, 5, 6. So what's the name here? Don't forget the 2, right, 2-hexanol. Right, because that OH could be anywhere, and so you have to put the 2. It could be on carbon number 1, right? It could be 1-hexanol. 2, it could be 3, right? How come it couldn't be 4-hexanol though?
Because we number.
Right, because if it were right here, you'd start numbering from the left. Good. Okay, here we go. Let's number 1, 2, 3, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yeah. So then we have our choices. Okay, numbering this way gives me 1, 2, 3. If I go this way, that gives me 2 substituents. If I number this way, that gives me 3 substituents, right? So which one am I going to pick?
1, 3.
The linear version, right? Because I want to pick the version that gives me the most substituents. So I number from here. Why am I not numbering from here?
Because the alcohol takes
Right, the alcohol takes priority over this methyl group. Good. So 1, 2, 3, 4, 5, 6. And now we just need to do all of our guests, right? All of our substituents. So this is a methyl group. This is a what group? Ethyl group, right? So we have to go alphabetically. So what's the name here?
4-ethyl.
4-ethyl.
5-methyl.
5-methyl.
6 or 2-hexanol.
2-hexanol, right? And then again, you could have written that as 4-ethyl 5-methyl hexane - 2-all. That would work as well. Good. You feeling good about this? Right. Nomenclature of alcohols is pretty straightforward, especially if you understand amines, then you understand alcohols. I think they're very, very similar. And like I said at the beginning of the semester, like that first lecture is kind of the worst, right? And then after that, it's really just variations on a theme. Oops. So let me pause it and let's try 2 that are in rings. Let's look at our 2 cyclics, see what we got. So, carbon number 1 is here, right? And now we just need to decide which direction we're going to number. We're going to number clockwise or counterclockwise? Right, clockwise. 1, 2, 3. So the name of this would be what? 3-ethyl. Now, do you need the 1? No, because it's by default number 1. So 3-ethyl cyclohexanol, right? You don't need the 1 because it's a ring and it's an alcohol. Therefore, that's default setting number 1. Now, in a minute, we'll talk about molecules containing 2 OH groups, and then you would have to designate where both OHs are. But here, because there's just 1, you don't need to put the 1. All right, there's no question that this is carbon number 1. Now we just need to figure out which way we're numbering. Which way? Counterclockwise, right. 2, 3, 4, 5, 6. So what's the name of this?
3, 4, 5,
3,4-dimethyl.
Cyclohexanol.
Right. Good. Feel good on naming and reams? All right. Okay, let's go the other way. I've given you some structures to draw. So here are two names. You take a stab at trying those. All right, let's see what we got. So octan tells me it's an 8-carbon chain, right? It's not cyclo, so it's linear. 1, 2, 3, 4, 5, 6, 7, 8. 2,4-dimethyl, so 1, 2, 3, 4, and then 3 octanol. Do we agree? And then let's do, this is a heptanol. How many carbons are in that chain? 7, and it's cyclo, so have fun drawing a 7-membered ring. I have to kind of think about drawing a 7-membered ring too. Okay, so that's carbon number 1. And then 3 bromo, 1, 2, 3. Do we agree? All right. All right, I think we can, yeah, we can skip on down to this. This is what we did last week with amines, and we're going to see it again with alcohols, primary, secondary, and tertiary. Right, so this will be a primary alcohol. It's a OH with just 1 carbon atom, right? So, for instance, this is the simplest alcohol you could have. This is methanol, right? This is CH3OH. That's a primary carbon. That's a primary alcohol. Or if this is a carbon and it's attached to some other chain or some other whatever, right? That's still an OH attached just to 1 carbon, right? Now, here will be a secondary alcohol. So a secondary carbon is a carbon that's in a chain, okay? So here, R just means the rest of the chain. So for instance, if this is CH2, CH2, CH3, and this is CH2, CH2, CH3, right? This carbon is attached to 2 other carbons. That makes it a secondary carbon. That makes this a secondary alcohol. This carbon would be attached to 1 other carbon. That makes it a primary carbon. That makes this a primary alcohol, okay? And then here, this will be a tertiary carbon if it's attached to CH2, CH2, CH3, CH2, CH2, CH3, CH2, CH2, CH3, right? Chain, all 3 directions. That's a carbon attached to 3 other carbons. That makes it a tertiary carbon. That makes that a tertiary alcohol. Can you have a quaternary alcohol? No, because how would you have a quaternary carbon? A quaternary carbon will be attached to 4 carbons, right? And then you have an OH in addition to that. And a carbon can't have 5 bonds, right? So let's just go over these verbally. What kind of alcohol? Primary, secondary, or tertiary? That'd be secondary. Good. What about this one? That'd be tertiary. Good. What about this one?
Primary.
Primary. Good. And then what about this one? It's in a ring. Well, what's that carbon attached to?
Oh.
It's attached to 2 other carbons, right? So it'd be a secondary. Good. All right, I think we can skip over this. Now, common names are something that you see. You see this TERT or T or SEC, SEC or S. That stands for tertiary, secondary. Okay, these are called common names. Those are not IUPAC names. I don't think your homework is going to ask for these, but I still like to show it to you, okay? So, for instance, this would be T-butyl alcohol because that is a 4-carbon configuration, and it's got the alcohol on a tertiary carbon. This would be S-propyl, right? Because there are 3 carbons that makes it propyl. And this is a secondary carbon where the OH is. But again, these are not IUPAC names, right? The IUPAC name of this would be what? 2-methyl, then what? 2-propanol, right? And then this would just be 2-propanol. Okay, now when you have more than one OH group, we're going to call it either a diol or a triol. So this is a diol. Okay, you do have to state where both OHs are, because they could both be on number 1, right? It could be 1,1 ethane at the diol, right? Or it could be 1,2 at the diol. All right, antifreeze. My car is leaking this at the moment, so I need to take my car to the shop. So let's do these just together. Let's just do these together. I'm not going to pause the recording. I'm just going to lower them down so I can write. Let me pause the recording real quick. All right, let's go over this one. So we've got a diol here. We've got 2 OH groups we have to contend with. Right? So we're going to number to give priority, and there are no other substituents. So 1, 2, 3, 4, 5, 6, 7. So this would be 2, 4, what?
Is it heptadiol?
Heptadiol, right. Heptadiol. Good. And then here, which way do we number? From the right or from the left? From the left, right. So 1, 2, 3, 4, 5. Right. So this would be what?
2-methyl.
2-methyl, right?
1,3-pentadiol.
Right. Good. And just for fun, so I don't have to make another one problem up, let's just pretend that there was another OH right here. What would the name be now? It'd still be 2-methyl, right? 2-methyl.
1, 2, 3.
1, 2, 3, right.
Triol.
Pentatriol, right. Pentatriol. Tri if there are 3. Okay, so diols and triols in terms of their nomenclature are going to be very, very, very similar. If I asked you which one is going to be the highest boiling point, the diol versus the triol is going to have the higher boiling point, right? Because it's got 3 sources of hydrogen bonding versus 2. So in terms of predicting their properties, in terms of nomenclature, I think alcohol nomenclature is not that bad. So let's just skip on down to some practice. Now, these are all structural isomers. Whoops. Gotta put the screen back up. This is something you'll see in the enrichment we do this week. Right? These are all structural isomers. Right? You can have structural isomers of alcohols. They'll have the same formula. Well, they have different boiling points. Could I separate this mixture? Yes, you could. Structural isomers can be separated. Right? Remember, conformations can't be separated because that's just caused by rotating. So if I stand on my right foot versus standing on my left, right? But if I put the OH group in a different spot, it is going to modify the intermolecular forces slightly, but it'll be enough that you could distinguish the boiling point difference. All right, so let's talk about reactions of alcohols. There are 3 that we're going to look at: combustion, dehydration, and in terms of redox, because oxidation reduction is called redox, right? We're just going to look at the oxidation half right now. When we get to aldehydes and ketones, we'll go back and do reduction then. Okay, so we're just going to do the ox part of redox right now. So combustion is something that I think everybody knows from Chem 1, Intro Chem, right? What's combustion a reaction with? It produces CO2 and H2O, but what's the other reactant you need? Oxygen, right. So combustion produces O2. Combustion requires O2, right? And it produces CO2 and H2O. And of course, obviously heat, this is exothermic. So for instance, flambe, you're burning the alcohol, you're burning ethanol, right? So combustion is just a reaction with O2, producing CO2 and H2O, because this is a hydrocarbon. Yes. And just to balance it, remember to balance it. That's all you need to worry about. Make your reactant product table the way we did in Chem 1. So let's just do this one together. If this is 2-nonanol, it's fun to say, right? We need what as our other reactant? 2-nonanol plus O2, right, produces CO2 and H2O, right? And now we just balance it. Our coefficients come out to be 2, 27, 18, and 20. I don't think we need to go through how to balance that equation, do we? That one's going to require a fraction. All right, let's talk about dehydration. So think back to when we did alkenes. When we did alkene hydration, what did we add? Water. So when we do dehydration, what do you think we're going to be removing? Water, right? Oh, I'm so dehydrated, I need to drink some water, right? I don't have enough water, I'm dehydrated. So when we dehydrate an alcohol, we're going to be removing H2O. We're going to be producing it as a product, in other words, right? We need as our catalyst heat and acid. So heat, you can just represent that as a triangle, and acid, we represent that as H+, right? Those are our two catalysts that we're going to need. And we're going to get our alkene back. So this is the reverse, the literal reverse of what we did when we hydrated an alkene, right? When we take an alkene and we do a hydration, we get an alcohol. When we take our alcohol and we dehydrate it, we get that alkene back. All right? And that's the generic, H+ and heat. You can just write delta. So we need H+, we need heat. Now, our other product is H2O, right? Don't forget that, H2O. Because we gotta obey the law of conservation of mass, right? If you're looking at your reactants, this single bond now becomes a double bond, and this OH and that H, they're gone, right? So I've got to obey the law of conservation of mass, and I need to put that H2O as my other product. Make sense? Now, here's where we have to look at major product and minor product, because we can get that double bond on either side of the OH. So a lot of times, you're going to have one major product and one minor product. Now, sometimes it won't matter. Here, there's only one carbon-carbon bond. So you're only going to get one product, right? Not going to matter. But the majority of times, you'll have two possible products. And so let's look at this one. The OH group is right here, carbon 1, carbon 2, right? So it's on C2. So you could have the double bond forming here, or you could have the double bond forming here, right? So this is the version that forms the double bond here. This is the version that forms the double bond here, right? You can form it on either side, and one of them is the major product, one is the minor product. All right, so Satsev's rule says the most substituted double bond is your major product. Most substituted, or greatest number of alkyl groups is how your book words it. So which one is more substituted or has more alkyl groups? Top one or bottom one? The top one, right? Because this one's got a double bond involving a methyl group, whereas this one's got a double bond. There's not any substitution going on, right? So this is our major group. This is our major product. This is the minor product. So if I put this on a test, I'd only be interested in you drawing the major product, okay? Unless I just for some reason asked what the minor product was, which I probably wouldn't. So greatest number of alkyl groups, or in other words, most substituted. So even in one like this, there is going to be a major product and a minor product. So there's 2-butanol. So the double bond could be formed here, or the double bond could be formed here. Why is this one the major product, this one the minor product? Well, because let's look at it. This is a double bond between carbon, carbon, and they each only have one hydrogen, right? Where here, this is carbon, carbon. One of them's got two hydrogens and one hydrogen, right? There are fewer hydrogens in here. This is more substituted than this one is. Now, you can't really call it a substitution when it's just the hydrogen atom. But do you see the point that I'm making here, right? Two hydrogens, that's on it, on the end versus on the interior. So this is our major product. And that's Satsev's rule. Now, in a cyclic molecule, again, it's still going to follow Satsev's rule, right? If I've got my double bond, and if I've got my OH here, I can make the double bond on this side or on this side, right? So here's where the OH group came off, and I had a double bond here. Here's where the OH group came off and had the double bond here. This one's the major group, right? This one's substituted. This one's a double bond. It's not substituted. Make sense? Okay, so let's try this one. I'll pause the video. Major product when 3-methyl-2-butanol is dehydrated. Just write the whole reaction. Good practice. Just write the whole reaction. All right, let's go over this one. 3-methyl-2-butanol dehydration. Let's just write the entire reaction. Okay, it's not going to stay there. Whatever. Not going to pick a fight with the screen, right? Because my experience, the screen wins. So this is 3-methyl-2-butanol. So 1, 2, 3, 4. So 1, 2, 2-butanol, 3-methyl. All right, so what's our catalyst? All right, we need heat and we need acid. Okay, so we could have the double bond form on this side or the double bond form on this side, the left or the right. Where's the double bond going to form? On the right. Why? All right, this involves a double bond with an alkyl group, whereas this one would not. And then what's our other product?
It would be on the other side.
No.
Oh,
it's the other product of the reaction. H2O, right. And then just to review nomenclature, what's the name of this? Let's name this. We're going to number from the left or from the right? Number from here? 1, 2 versus 1, 2. Okay, why? Exactly. So 1, 2, 3, 4. So what's the name of this? 2-butene, right. Good. How do we feel about dehydration? Right, this is the opposite of what we learned, right? And if we go the other direction, right, we'll look at what we've already done that reaction, so I guess we'll go over it. All right. So that was an alkene reaction section.
For combustion, they need power.
You need activation energy in the form of heat, so some sort of spark. That's about it. All right, do 2-propanol dehydration. Write the full reaction. All right, let's go over this one. All right, that was the one we were doing, 2-propanol, yes? Yes, that was what we were doing. Okay, so I'm just going to leave the screen up. So we're doing 2-propanol dehydration. So 1, 2, 3, 2-propanol. Catalyst would be heat and acid. Is Satsev's rule going to apply here? No, right? There's only one product and one organic product, right? Because if you put it like this, or if you put it like this, are they the same molecule? Yes, they're the same. And then what's our other product? H2O. And what's the name of this? It's just propene, right? Is a 1 necessary? No, because there's only one place a double bond could be if there are 3 carbons in the chain. Good. All right, let's do another one. 2-methyl, I can just move it down. Oops. There you go. Dehydration of 2,4-dimethylcyclohexanol. I'll pause the recording and let's try this one. All right, let's go over this one. 2,4-dimethylcyclohexanol. Okay, so hexanol would be 6. Cyclo means it's in a ring. So OH is number 1. So that's 2, 3, 4 dimethyl, right? And we need heat and we need acid. Is Satsev's rule going to apply? Yes, it is, right? Because I could get the double bond here, or I could get the double bond here, on the right versus on the left. Which one is the winner? On the right. So we get this plus H2O. And let's just practice our nomenclature. How are we going to name this? Numbering has to go through the double bond, right? So 1, 2, 3, 4, 5, 6. So what's the name of this?
2,4-dimethyl 1-hexene.
Cyclohexene, yes. Right? Now this isn't a diene, right? In a diene, if it was, for instance, there was a double bond here, then you'd have to state carbon 1 and carbon 3 or whatever, right? Because if this were a diene, you'd have to number this way. And you'd have to state 1, 3 or whatever. But if there's only one double bond, you don't need to put the 1. If it's cyclic. If it's cyclic. Good. All right. I think I've got one more to practice on dehydration. Yep. So let me just move it down so I don't have to play with the screen. Dehydration of 3-ethyl 2,5-dimethyl 2-heptanol, and then name it, which we've been naming anyway. So I'll pause the recording here. All right, let's do this one. Heptanol, 7, and it's not cyclic, so it's just straight chain. 1, 2, 3, 4, 5, 6, 7. 3-ethyl, 1, 2, 3. 2,5-dimethyl, 2, 3, 4, 5, and then 2-heptanol. All right, so we need our catalysts. Is Satsev's rule going to apply? Yes, it is, right? Is it going to be on the left or on the right? On the right. 1, 2, 3, 4, 5, 6, 7. So all of our substituents are still there. Now we need our double bond. And then we need our H2O. All right. Numbering still needs to include, boy, that got a little carried away. Numbering still needs to include the double bond, right? So are we numbering from the left or from the right? From the left, right? 1, 2, 3, 4, 5, 6, 7. So this is what? 3-ethyl 2,5-dimethyl 2-heptene, right? Good. All right, so you're feeling good about dehydration? All right, the next and last reaction that we're going to talk about with alcohols is oxidation. We'll do the reduction portion when we get to the aldehydes and ketones section. So we're only doing the oxidation portion. So when we oxidize an alcohol, we're either going to get an aldehyde or a ketone, depending on if it's primary or if it's secondary. Okay, so primary alcohol is going to give us an aldehyde. Secondary alcohol is going to give us a ketone, and we can't oxidize a tertiary alcohol. It won't work. I'll show you why. So the way that we represent that is we put an O with brackets, unless I tell you what the oxidizing agent is. So if I say it's oxidized using KMNO4, then you'd write KMNO4. But if I don't say what the oxidizing agent is, I just say show the reaction of oxidation, you just put O in brackets. Okay? So primary alcohol, this is a primary alcohol, right, because it's attached to one other carbon, it's primary carbon, becomes an aldehyde. Okay? And then our other product is H2O. Okay? So this OH becomes a C double bond O. Okay, you're making the alcohol into an aldehyde. And then if it's a secondary alcohol, this is a secondary carbon, right? Because it's on a carbon, it's a carbon that's attached to two other carbons. So when we oxidize it, again, I didn't tell you what the oxidizing agent is, so you can just put O in brackets if I don't tell you what it is. This produces a ketone because a C double bond O, that functional group's a ketone, right? It's on the interior, whereas an aldehyde is on the end. Okay? And again, H2O is our other product. Now you can't oxidize a tertiary alcohol, no reaction, right? You can throw any oxidizer you want at this and you're not going to get a reaction. Why? Why couldn't this become oxidized? Make a C double bond O here. What would happen? This is a tertiary carbon, right? It's got 1, 2, 3, 4 bonds already. You can't have a carbon with 5 bonds, right? We're not oxidizing. There's no hydrogen here to oxidize. Okay, so this is just a pattern, right? If it's a primary alcohol, you're going to get an aldehyde, and if it's a secondary alcohol, you're going to get a ketone. Now, we don't know how to name aldehydes and ketones yet. That's coming up soon, so I won't make you name these products yet. But by the time we get to exam 2, you'll be able to name them. And then reduction is the opposite direction, so we'll worry about it. That's going this way. So when we get to aldehydes and ketone reactions, we'll do reduction and we'll go back to alcohols. All right, so this is where we go. This is what we're doing right now. Another reaction we'll do in aldehydes is we can further oxidize those aldehydes into carboxylic acids. And then we can go back all the way back to our alcohol again, right? So we're just doing this piece right now. We can further oxidize it, and then when we do reduction, we can go this direction. So why don't you try this one? Show the oxidation of 2-ethyl, 3-methyl-cyclohexanol. And since you don't know how to name it yet, just identify what functional group is in your product. All right, let's go over this one. All right, 2-ethyl, 3-methyl-cyclohexanol. So that's a 7-carbon chain, and it is in a ring, right? 7-membered ring, 2-ethyl, 3-methyl, and then carbon number 1 is obviously where our alcohol is. So what functional group do we get in this product? Is that an aldehyde or a ketone? That's ketone, right? Because a ketone is always on a secondary carbon, right? This is a secondary carbon. Aldehyde, if it had an aldehyde would be on an end. Right? So an aldehyde would be on the end. It'd be on a primary carbon, whereas a ketone is always on a secondary carbon. Now, you don't know how to name ketones yet, so I wouldn't ask you to name this. Why don't you try this one? Show the oxidation of 3-bromo-1-hexanol, and then identify the functional group in this product. All right, let's go over this one. So this is not cyclic, right? This is 3-bromo-1-hexanol. So it's nice and linear. Our functional group that we get here is aldehyde or ketone. That's an aldehyde, right? Because this is primary carbon. This is always on the end. Aldehydes are on the end. If we were a ketone, it'd be here or here or here, right? Aldehydes are on the ends. Good. All right, I've got a couple more practice problems. So I think what I'm going to do, I'm actually going to put them all on one slide, and then we'll go over them all together. So let me just pause the video for a second and put them all on one slide. All right, I put all the problems on one slide, so we don't have to go through a whole bunch of slides. I can now pause it, and you can write 4 reactions for me. So number 1, you're going to write 2 reactions, 1 for oxidation and 1 for dehydration of 3,4-dimethyl-2-heptanol, including any catalysts. So ask yourself, what's oxidation? Ask yourself, what's dehydration? And then do that again. Show me the oxidation reaction and also show me the dehydration reaction of 2-ethylcyclohexanol. So 1 is cyclic, 1 is linear. So you should have 4 reactions in total. I'm going to pause the video, give you a chance to try these, and then we'll go over it. And these will be the last 4 that we're doing today. Let's go over these now. So our first reaction, well, our first molecule, I should say, I'm going to write 2 reactions here. 1 for oxidation, 1 for dehydration. So this is 3,4-dimethyl-2-heptanol. So hep is 7, 1, 2, 3, 4, 5, 6, 7. 2-heptanol, 3,4-dimethyl, 3,4-dimethyl. All right, let's do the oxidation first. I didn't tell you what the oxidizing agent is, so we just put O in brackets. All right, what are we going to get? Aldehyde or ketone? This will be a ketone, right? 1, 2, 3, 4, 5, 6, 7. We get a double bond O, and then our substituents transfer along with it. And what's our other product? H2O, right? So there's the oxidation. And then for the dehydration, what catalysts do we need?
Acid and.
Okay. Does Satsev's rule apply?
Yes.
Yes, it does. Is the double bond going to be on the left or on the right?
On the right.
On the right. 1, 2, 3, 4, 5, 6, 7. So we're going to have this, right? And what's our other product?
For dehydration.
For dehydration, yep.
Water.
Water. How do we feel on this one? Okay, 2 reactions. And then the last problem we're going to do for today, we're doing 2-ethylcyclohexanol. We're doing the same thing. We're writing 2 reactions. Cyclohexanol would be a 6-membered ring. 2-ethyl, 1, 2. So this would be number 1. So let's do oxidation first. I didn't tell you what the oxidizing agent is. So just put O in brackets. Are we getting an aldehyde or a ketone?
Or maybe
Ketone, right. Ketone, because that's a secondary carbon. So my substituent doesn't go anywhere. I get a ketone plus what? H2O. And then to do the dehydration, my catalysts are still heat and acid, right? And what am I going to get? My substituents transferred. Does Satsev's rule apply? Are you sure?
Oh, yes, it does.
It does apply, right? Because if I put the double bond here, that's more substituted than if I put the double bond here, right? So I get this plus H2O. You don't know how to name this. You do know how to name this. Feeling good? All right, that's where we're going to stop for today. So on Friday lecture, we'll be doing enrichment problems.